I just want to say this at the beginning today, since I have a lot of newer subscribers, and not everyone watches to the end screen. If you want to support this channel further, you can consider joining my Patreon, purchasing some of my Teespring merch, or purchasing some of my fiction novels on Amazon. All of the links are below, and of course if you choose not to, please don't feel bad about it. Your continued viewership is more than enough. Mars. The single most explored planet in our solar system, with the obvious exception of Earth, at least the parts of Earth that are above the water. While NASA and other agencies have made some effort to explore every intrasolar planet over the last 60 years, there is only one that has had a more or less continuous human presence on it since the 1990s. Only one that we have understood and mapped and cataloged so intimately. Only one that we are likely to see human boots on within this century. Mars. Today we're going to do a rundown of every effort to explore Mars that's ever been undertaken, beginning with just looking at it from afar, and ending with what the future may hold. This is a pretty extensive list. While some efforts have failed, others have surpassed expectations and kept going for literal years after the end of their proposed missions. There is a lot to cover here, so strap yourselves in and brace for liftoff. Quick disclaimer, I will be frequently referring to time spent on Mars using the Sol unit, which is 1 day on Mars. Due to the difference in orbit around the Sun, 1 day on Mars, 1 Sol, is equivalent to 1 day and 37 minutes on Earth. A small difference, but one that adds up over time. Human beings have been observing Mars from Earth for a very long time. The first peoples to notice that Mars appeared to be different from the other stars were ancient Egyptian astronomers in the 2nd millennium BCE. They managed to track its retrograde motion in the sky, which is to say, as the orbits of the two planets line up, Mars will, due to having a slower orbit around the Sun, appear to briefly move backwards in the sky, creating a small loop when mapped out like this. By around the 8th century BCE, astronomers of the Neo-Babylonian Empire began charting the synodic period of Mars, essentially noticing that it made its looping circuit across the sky every 2.1 years. Of course, they didn't quite understand its orbit around the Sun being the reason for this period, but they were able to accurately track and predict where and when it would appear in the sky. The Chinese Zhou dynasty of 1045 BCE began to make note of planetary conjunctions, including those of Mars. This is when two planets would get close enough for one to be obscured by another. They noted that in 368, 375, and 405 CE, Mars was obscured by Venus. In ancient Greece, the movement of the 7 celestial bodies began to be coalesced into a more coherent model, though it was a geocentric one with the Earth being at the center. Plato defined the orders of the planets from nearest to most distant to be the Moon, the Sun, Venus, Mercury, Mars, Jupiter, Saturn, and the fixed stars. Despite being horribly wrong, he did correctly assume that an object's motion depended on its distance, with the most distant objects moving slower around their parent object. Very simple observations could confirm some of these notions. Aristotle, for instance, noticed that Mars would pass behind the Moon and therefore must be further away. By the 2nd century CE, Roman mathematician Ptolemy further refined the solar system model by attempting to address the problem of Mars's orbit, as it appeared to move faster on one side of its orbit than the other, which conflicted with Aristotle's model of uniform motion. He concluded the order of the planets to be the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Getting closer, but still not quite there. In the 5th century, Indian astronomers began to estimate the size and distance of Mars more accurately, using its angular size in the sky to deduce that it was 10,433,000 kilometers away, which was off by about 200 million kilometers, and its diameter to be 6,070 kilometers, which is actually fairly close, off from the modern value by only about 700 kilometers. It wouldn't be until 1543 that a lot of cosmic problems began to be solved by Copernicus's heliocentric model, which placed the entire solar system, including the Earth, in orbit around the Sun, between Venus and Mars. His proposal finally placed the planets in their correct order based entirely off of the solar orbits, and while people were slow to accept it, he was, of course, correct. In the next century, telescope observations of Mars began. Galileo in 1610 began making Mars observations, and while his equipment couldn't resolve any surface details, he hoped to see if Mars showed any phases like Venus or the Moon. He never quite got there, but did manage to determine that Mars changed angular size throughout the year as it came closer or more distant from the Earth. Only 35 years later, Polish astronomer Johann Hevelius succeeded, observing a phase of Mars through his telescope. However, due to it being further out from the Sun than Earth, outer planets like Mars only have small changes in phase from our perspective. As telescope technology refined, astronomers such as Christian Huygens began to notice dark patches on the surface of Mars, and while they couldn't confirm with any detail, what they were seeing were shield volcanoes as well as its polar ice caps. Using these surface features, they also began to calculate the rotation period of Mars, believing it to be similar to the Earth, around 24 hours. In the 1700s, astronomers noted that the size of Mars's polar caps seemed to vary over time, eventually coming to the conclusion that Mars had seasons like Earth's, and that the caps shrank in the Martian summer and expanded in the winter, as well as concluding that they were probably made of ice. They also began to notice that its surface features were occasionally obscured completely, though they didn't understand that this was due to global dust storms, and that Mars definitely had some kind of atmosphere surrounding it, as its edges were somewhat fuzzy. In 1877, Italian astronomer Giovanni Schiaparelli observed several long straight lines along the equatorial region of Mars. He referred to them as canali, which means channels, and this term was later mistranslated as canals. At this time, astronomy involved no photography. Telescope operators would simply spend hours observing through the lens, waiting for the clearest moments to later produce drawings and maps of what they saw. The primitive technology and lack of precise ability to capture it led to several misconceptions, such as the darker areas on the surface to be oceans, and the haze around the planet to be an indication of a very thick atmosphere. This, combined with its size and axial tilt being similar to Earth, as well as the shrinking and growing ice caps, led to a belief that it was possible Mars could contain life, or at least once did. Seasonal changes in its surface were hypothesized to indicate the seasonal growth of plant life, though most of it was actually caused by dust storms. In 1894, Schiaparelli's canals, as they were now being called, were hypothesized to be an irrigation system, made for transporting water from the planet's poles to the more habitable regions. Speculation became abound that an advanced alien race had constructed these canals, and that they may or may not still be living on the planet. Very early on, as early as 1909, the notion of these canals came into question, with the Meudon Observatory seeing none on the surface when they looked. Spectroscopic analysis began to show that there was likely no water present in the Martian atmosphere, and further research suggested the temperature and atmospheric pressure to be far too low for liquid water to exist on the surface. Many began to conclude that complex life was impossible, as was the plant-bearing irrigation system suggested. However, the idea would persist that there could be, or once was, life on Mars, all the way up to the space race of the 1960s, despite astronomers over the last 50 years concluding that the perceived canals were actually nothing more than optical illusions caused by poor quality telescopes and their tendency to cause point-like features to coalesce into apparent lines. The idea went so far as to be the prime inspiration behind the H.G. Wells novel War of the Worlds, in which highly advanced Martians had exhausted the resources of their planet and were now targeting Earth as the next opportunity to do it again. By the late 1800s and early 1900s, telescope technology had improved enough that large observatories began producing maps of Mars, carefully sketching out what they could see of its surface and speculating as to what it all actually was. At the same time, other astronomers used the parallax of Mars from various locations to more accurately determine its distance from the Earth, and noted that Mars appeared to have two small objects orbiting around it, the moons Phobos and Deimos. Throughout the 1900s, more refined technology allowed previous assertions to be disproven, such as the speculation of large amounts of water vapor in the atmosphere, as well as explaining the obscuring of its surface caused by wind-blown sand or dust. Using thermocouples attached to their observatory telescopes, American astronomers Seth Barnes Nicholson and Edison Pettit were able to determine the relative temperature range of Mars. A few years later, Dutch astronomers estimated the mass of Mars using the motion of its moons, coming within 0.2% of the true figure. By this point, spaceflight was just around the corner. Almost as soon as satellites and human beings were sent into Earth orbit, plans were being made to push them out further, to explore the Moon, Mars, and beyond. It took several thousand years from the beginning of observations, but the next 60 years would bring us closer to Mars than ever before. There's nothing quite like going there and seeing it for yourself. Let's begin to deconstruct the first attempts. The first nation to attempt to explore Mars was the Soviet Union, dubbing their program, appropriately, the Mars Program. However, these first attempts did not go very well. At this time, the Soviets tended to give special designations for missions that failed before getting very far, meaning that the first 3 attempts didn't actually carry the Mars designation. The first attempt was called IM-1, named for its spacecraft, and was launched on a modified new variant of their staple R-7 rocket called the Molniya rocket. The spacecraft, intended to perform a flyby of Mars, carried a range of equipment: an ultraviolet spectrometer, a radiation detector, and a cosmic ray detector. 2 more pieces of equipment were removed due to mass constraints: a television imaging system and a spectroreflectometer. IM-1 launched on October 10, 1960, and its first stage functioned well, but the rocket's second stage experienced intense vibrations that damaged gyroscopes on the third stage, causing that third stage to point below the horizon, never quite reaching orbit, and disintegrate over Siberia as it re-entered the atmosphere. IM-2 was up to bat only 4 days later. It featured an identical spacecraft with identical equipment and an identical carrier rocket. While it was being prepared, the second stage experienced an oxidizer leak. The supercooled liquid oxygen spilled around the engine's fuel valves, causing it to freeze the refined kerosene propellant. As a result, after the first stage had done its job, the second stage failed to ignite entirely, and the rocket crashed back down to Earth. 2 years later, a new spacecraft was developed, the Mars 2MV-4, again launched on a now improved Molniya rocket. The spacecraft was a little simpler, carrying only 2 instruments to be used on a Mars flyby: an imaging system and a magnetometer. This time, the spacecraft managed to reach low Earth orbit. However, when the upper stage ignited to push it further, lubricant leaked out of the turbopump and it seized up. This caused an explosion in the main engine, which destroyed both the upper stage and the spacecraft. This created 22 pieces of debris that would re-enter the atmosphere and disintegrate by February of the next year. 8 days after this failure, the first launch to carry the Mars designation was carried out. Mars 1, largely identical to the previous spacecraft, was launched on November 1, 1962. These spacecraft were modified from the Soviet Venera spacecraft that were used to explore Venus in a cylinder shape around 11 feet long and 3.3 feet in diameter. It had 2 main components. The upper module contained guidance and onboard propulsion, while the lower module contained scientific instruments. Attached to the sides were a parabolic high-gain antenna for communication, as well as an omnidirectional antenna and a semi-directional antenna. Power came from 2 solar wings on either side and was stored in 42-amp batteries. Mounted on the ends of the solar wings were radiators to regulate the spacecraft's temperatures. The instruments were more beefed up as well. In addition to the imaging system and magnetometer, this one had a spectrograph to study ozone absorption and a micrometeoroid instrument. This time the launch went according to plan, and the spacecraft was sent into an orbit around the Sun that would eventually lead it to Mars. However, it was quickly detected that the spacecraft was suffering a leak in gas valves for its orientation system, and control was switched to gyroscopes. It continued to make automated transmissions to the ground, first every 2 days, then every 5 days. However, after nearly 5 months at a distance from Earth of around 106,760,000 kilometers, or 66,340,000 miles, communications abruptly ceased, likely due to the failure of the antenna system. While they could no longer talk to it, it would have made its closest pass by Mars around 3 months later, at a distance of 193,000 kilometers or 120,000 miles, before being sent back into orbit of the Sun. While also technically a failure, Mars 1 did send back some valuable data. It recorded micrometeoroid strikes almost every 2 minutes due to being launched into a meteor shower, as well as detecting solar wind and confirming the magnitude of the Van Allen radiation belts around Earth. The Mars program would make one more attempt before experiencing success with another flight that never made it out of Earth orbit. More or less identical to Mars 1, this one again made it into Earth orbit. However, at some point during the launch, a number of failures in the propellant feed lines resulted in a fuse to come loose in the upper stage's engine system, and as a result, it never ignited and was left in its parking orbit to decay. The USSR's first 4 attempts to explore Mars had, more or less, failed completely. Now, it was NASA's turn. Beginning in 1960, NASA started a new program to begin exploration of deep space, Mariner, targeting the nearest planets of Venus and Mars. The goal was to take advantage of the soon-ready Atlas launch vehicle and produce a series of cheap probes that could be launched with high cadence outside of the Earth-Moon system. The first 2 Mariner spacecraft were heavily based on the earlier Ranger lunar probes, but all were centered around a bus shaped like a hexagon or an octagon, which all of the components were then attached to. These first R-class spacecraft were dedicated to flybys of Venus, and since that isn't the subject of today's video, we're going to skip ahead to Mariner 3 and 4. These 2 craft, both identical, improved on the R-class design with a larger new bus with 4 solar panels instead of 2, as well as a TV camera, new instrumentation including a magnetometer, a plasma probe, a cosmic ray telescope, a trapped radiation detector, a cosmic ray ionization chamber, and a cosmic dust detector. Mariner 3 launched on November 5, 1964. Its Atlas Agena launch vehicle performed nominally at first, placing the vehicle into its parking orbit, and then making its second burn to push the spacecraft toward Mars. 1 hour later, Mission Control began receiving data, and the scientific instruments were functioning, but the solar panels were not. They weren't exactly sure what was wrong, so some systems were shut down to save power while they investigated. Examining the telemetry showed the velocity was below normal, which led them to the conclusion that the payload fairing around the spacecraft had failed to separate. They sent a command to manually jettison the shroud, but nothing happened. The spacecraft had its own small propulsion system, meant primarily for course corrections, and the next consideration was firing that system in order to push the shroud away. However, the batteries in the probe died before the go-ahead was given, and the mission was officially lost. Mariner 3 would miss Mars by several million miles. Mariner 4 was launched 3 weeks later, this time with much more success. A new fairing had been developed to hopefully avoid the previous mission's problems, which caused increased weight and therefore further improvements to the Atlas booster to loft it into orbit. The work was completed just in time for the end of the Mars transfer window, and Mariner 4 lifted off successfully, jettisoning its payload shroud and heading for Mars. Mariner 4 used an instrument called a Canopus star tracker which, as you might be able to tell, locks onto the star Canopus for use as a navigational aid. Once the spacecraft knows where Canopus is, it knows how it's oriented in space, allowing it to maintain the ideal attitude during its cruise to Mars. However, Mariner 4's star tracker had some difficulty locking onto Canopus. It was designed to respond to objects within a certain brightness range that Canopus is in, but as it turned out, there were 7 objects visible to it that fit the bill. It took a full day of hopping around to different stars, as well as some stray lights reflecting off of the Earth itself, to finally find and lock onto Canopus. It then proceeded to constantly lose this lock when the spacecraft would roll slightly, and its first course correction maneuver was aborted for this same reason. After 3 weeks and 6 losses of Canopus lock, it was concluded that small dust particles were floating around near the spacecraft, and when they reflected light, this would confuse the sensor as they passed between it and Canopus, even sometimes convincing it that it was no longer locked onto Canopus, forcing it to go back into a searching mode. Despite efforts to modify the star tracker's software, these errors continued 38 more times on the way to Mars. On July 4, 1965, 228 days after its launch, Mariner 4 became the first spacecraft to successfully perform a flyby of Mars. Over the next 48 hours, it would pass within 10,000 kilometers of the planet's surface, its instruments being powered up and taking various readings of the planet and the area surrounding it. On July 15th, it made its closest approach, its camera taking 21 full images and most of a 20-second image, showing the world as barren craters, empty plains, and thin atmosphere for the first time through something other than a telescope. It wasn't immediately able to transmit these images back, so while it was doing work and flying past the planet, employees at JPL did something very interesting. A real-time data translator machine converted the first image into numbers printed on strips of papers, and the workers took these strips, attached them side by side to a display panel, and hand-colored the numbers like a paint-by-numbers picture. The results of the images were very surprising to a lot of people. Craters had been predicted by some, but not universally accepted as a likelihood, nor was the frequency of them. There were no canals, which was less surprising, but the surface of Mars looked a lot more like the surface of the Moon than had been expected. Instruments recorded measurements of the atmosphere, showing it to be much thinner than had been expected as well. Mars was now more or less confirmed to be a fairly inactive planet, unprotected from the harshness of space and the things that came from space. Hopes of finding intelligent life on Mars were largely dissipated now, though some held out hope, insisting that the images were too low resolution and taken from too great a distance to make any definite claims. Well before the next Mars Mariner mission was ready, in fact before Mariner 4 even performed its flyby, the Soviet Union launched Zond 2, which was not even close to the second spacecraft in the Zond program, which had both explored the Moon and attempted to explore Mars and Venus. Though it reached orbit and performed its injection burn successfully, communications were lost before it reached Mars in May of 1965. It passed by the planet closer than Mariner 4 had, coming within 1,500 kilometers of the surface, but it was no longer in contact with Earth and could no longer send back any data, and was therefore considered a failure. It would be 5 years before another Mariner mission was performed, Mariner 6 and 7, the first dual mission to Mars in 1969. The goal was to expand the work already done by Mariner 4, get closer, look at new areas, and send back even more data. Constructed similarly to the previous probes, this time with a 2-axis scan platform mounted beneath the octagonal bus, with all of the scientific instruments being kept there as well. These instruments were significantly beefier than the previous series, with 8 specific functions including the TV camera. It was able to transmit data back at an increased rate using new communication systems, and had a higher capacity for storing data with an analog tape recorder capable of holding around 24.3 megabytes of information. Just over a week before launch, Mariner 6 suffered a near disaster that was saved only by some very quick thinking. During a dress rehearsal that had electrical power running but didn't load the booster with propellant, a malfunction opened 2 valves in the booster, which release helium from inside. Helium was used to pressurize the booster's balloon-like skin, and it quickly began to crumple over from the loss of pressure. However, 2 pad technicians, Bill McClure and Charles Beverlin, activated a manual override switch, which closed the valves and repressurized the booster. Mariner 6 and its Centaur upper stage were saved, but the booster was not. The loss of pressure, even over the course of a few minutes, caused structural damage that prevented it from being reused, so it had to be replaced. Mariner 6 and 7 launched roughly 1 month apart, on February 25th and March 27th respectively. Launch and injection burns were nominal, after which both Centaur upper stages turned around and performed another burn, both to get them and their cryogenic fuels away from the probes, as well as keep them from crashing into Mars. After the Surveyor probes to the Moon had been found to have Earthborne bacteria on them, NASA adopted strict policies to prevent contamination of other planets, and not crashing upper stages into Mars was part of those policies. With less than a week to go before reaching Mars, JPL had a problem. Contact was lost with Mariner 7. Mission Control switched the probe to its low-gain antenna, reacquired the signal, and then switched back to the high-gain shortly after Mariner 6 made its encounter with Mars. It was believed that some kind of gas leak had occurred, and when a battery later failed, the leak was considered most likely to be traced back to that battery. Despite the momentary concern, Mariner 7 was reprogrammed, focusing on new areas of opportunity that had been missed by Mariner 6, resulting in it returning even more data than its sister spacecraft, despite the battery failure. On July 31st, Mariner 6 made its closest approach to Mars, with Mariner 7 doing it 5 days later on August 5th. Both probes passed at a distance of around 3,430 kilometers from the surface. Together, they managed to photograph almost 20% of the planet's surface, giving clear views of the darker regions initially thought to be oceans in the past, and showing the variations to be nothing more than different composition of materials. While the reasoning isn't entirely understood even today, there are a number of natural explanations ranging from Martian winters pulling darker material from under the surface to areas that have simply not been exposed to the atmosphere to cause chemical-induced weathering. Mariner 7 also flew past the Martian South Pole, giving clear views of the ice-filled craters. The clarity of the images drew a further line in the sand between the similarities with Mars and the Moon. While both had a lot of crater impacts, there was clearly a lot going on in terms of weather when it came to Mars. The crafts also returned data to identify the composition of the polar caps as primarily carbon dioxide, confirm the surface pressure from the atmosphere, and refine estimates of the mass, radius, and shape of Mars. The 2 spacecraft working in tandem also proved invaluable, allowing Mariner 6 to function as a kind of test run, making Mariner 7 the more efficient of the 2 probes, returning more data and images than the first. Following their mission, both craft went into heliocentric orbits and are now defunct. Job done. Following 2 more Soviet launch failures of the Mars program probes, Mariner 8 and 9 were next. While largely similar to the previous series in terms of structure and instrumentation, they featured beefed-up propulsion systems capable of producing 1,340 newtons of thrust and being restarted up to 5 times. The reason for this was simple. These spacecraft would no longer be doing simple one-time flybys of Mars. Now, the goal was to get into Mars orbit. As a result, their imaging systems were also vastly improved, now hoping to take more detailed photos of the Martian surface in the much larger stretches of time that they would be able to do so. Mariner 8 launched on May 9, 1971. Its booster phase was nominal, but around 265 seconds into ascent, the upper stage Centaur engine ignited and it began to pitch up and down, quickly tumbling out of control. This movement caused sloshing of the propellant within the tanks, which starved the engine of fuel and caused a premature shutdown around 100 seconds later. Well short of a nominal orbital insertion, Mariner 8 re-entered the atmosphere and fell into the Atlantic Ocean about 560 kilometers north of Puerto Rico. Before Mariner 9 would launch, the Soviet Mars 2 and Mars 3 probes would launch 10 and 18 days after Mariner 8. We'll come back to this, but this would be the beginning of a degree of success for the Soviet program, but we're not quite there yet. Mariner 9 was launched on May 30th, just behind the two Soviet probes. Extra testing was conducted to ensure the probe wasn't interfering with the Centaur stage, but the previous failure was deemed to be unrelated to the probe itself. Mariner 9 successfully reached orbit, performed its injection burn, and separated from the Centaur upper stage at 13 minutes 18 seconds after launch. While its journey to the Red Planet was fairly uneventful, when Mariner 9 arrived at Mars on November 14, 1971, it encountered an unusual problem. Not with the spacecraft, all was nominal there, but with the planet. Mars was completely covered in an unprecedented massive dust storm, making its surface features all but invisible. Thus, Mariner 9 turned around and fired its propulsion system, becoming the first spacecraft to enter orbit of another planet, beating the Soviet Mars 2 by just over a week, but it wasn't about to start all of its work just yet. It moved around the planet at an altitude of 1,398 kilometers at the lowest and 17,916 kilometers at the highest at a 64-degree inclination. Mission Control reprogrammed Mariner 9's computer to delay taking most images of the surface, waiting for the dust to clear up for several months. However, at the same time, they did take the opportunity to take the first close-up images of a dusty Mars, noting a number of taller features that poked through the dust while the storm was dying down. The situation presented a strong case for being able to orbit the planet rather than just fly by. In the latter situation, Mariner 9 would have been able to obtain very little information. Midway through January of 1972, the dust storm had mostly ended, and the main imaging began. The results were spectacular. More craters, what appeared to be dried riverbeds, and massive extinct volcanoes, including the largest known volcano in the entire solar system. Olympus Mons, previously noticed by astronomers as one of the only features visible during dust storms, is over 21 kilometers tall, 3 times the height of Mount Everest, with a base that's over 600 kilometers across, dwarfing any volcanoes on the Earth. Another major surface feature that was shockingly missed by all previous probes and identified by Mariner 9 was Valles Marineris, an extravagant system of enormous canyons that stretched 4,000 kilometers across the surface and, in some areas, dived down a full 7 kilometers in depth. Over the course of 349 days, Mariner 9 transmitted a total of 7,239 images, covering around 85% of the Martian surface. It found evidence of wind and water erosion, deposits of material left by the same erosions, fogs, clouds, and even photographed Phobos and Deimos, Mars' 2 small moons. By October 27, 1972, the gases it used for attitude control were depleted, and Mariner 9 was officially switched off, its mission complete and wholly successful. It remained in orbit for decades, but as of just 2 years ago, most likely re-entered the atmosphere and crashed into the Martian surface. Thus ends the most important early success of Mars exploration, paving the way for future NASA missions. But before we get back to that, let's briefly head over to the land of hammers and sickles. Mars 2 and 3, much like previous missions, launched 9 days apart, on May 19th and 28th, 1971. Despite being ahead of Mariner 9, their less powerful upper stage propulsion resulted in a longer journey to Mars, making them the second and third place to successfully orbit the planet. Roughly identical spacecraft, these were significantly more elaborate than previous probes in the Mars program, consisting of 3 distinct modules: an orbiter, a lander, and a rover contained within the lander. They used the same bus as the Soviets had for their Venera-Venus program, and had instruments with similar goals to the Mariner 8 and 9 series. Image the planet, measure the atmosphere and magnetic fields, as well as act as communication relays between their lander modules and the Earth. The landers were spherical modules with a heat shield on the bottom, the top opening up like flower petals after landing, and used a combination of retro rockets and parachutes for descent to the surface. The rovers, attached to an arm of the lander and tethered with an umbilical, are quite possibly the cutest thing you'll ever see. Since the properties of the surface and how to traverse it effectively were practically unknowns, the Prop M rovers used a set of skis that would daintily lift it across the surface in steps. Because they couldn't easily be controlled from Earth due to the roughly 20-minute communications delay, they used metal rods for obstacle avoidance and carried instruments that would measure the composition and density of the soil. No longer relying on R7 variants for launch vehicles, Mars 2 and 3 were lofted to orbit on Proton K heavy launch vehicles, their Block D upper stages sending them on a trajectory toward Mars. Mars 2 arrived just under 2 weeks after Mariner 9. However, unlike the NASA probes, Mission Control was unable to reprogram the orbiters, immediately detaching landers and beginning to take photos of the featureless, dust-obscured surface. The data, however, did reveal atomic hydrogen and oxygen in the upper atmosphere, as well as record surface temperatures and pressures, water vapor concentrations, and measured the height of the dust storms as being around 7 kilometers into the air. Meanwhile, the lander module descended into the Martian atmosphere at 6 kilometers per second. A quick note about how landing on Mars works. Due to the communications delay, these landings cannot be modified on the fly when the situation changes. Everything has to be pre-programmed in advance, and the controllers have to simply hope for the best while they wait 20 minutes to see if it all worked out. In the case of Mars 2, it didn't. Possibly due to a steep re-entry angle, it isn't exactly known, something on the lander malfunctioned and it didn't deploy its parachute. As a result, Mars 2 became the first man-made object to crash into the surface of Mars. Attempts to contact it afterward were unsuccessful. Mars 3 fared better. Sort of. Suffering from a partial loss of fuel, it placed itself into a more elliptical orbit than intended, taking almost 13 days to circle the planet. The dust storm caused similar problems with its imaging capabilities, and its lander also separated immediately after the probe was placed into orbit. Entering at a similar speed to Mars 2, the lander functioned normally this time, deployed its parachutes, and fired its retro rockets, becoming the first spacecraft to soft land on Mars on December 2, 1971. It quickly opened up, deployed its instruments, and began operations, beginning to transmit back to the orbiter after 90 seconds. However, 20 seconds after that, transmissions promptly stopped. The lander was dead before it could deploy its rover, transmit any useful data, or even transmit any useful images. 70 lines of an image of the surface was sent back, showing nothing more than a gray background with no details. It's unclear exactly why it failed. The dust storm is a popular candidate for damage during descent, but since they couldn't exactly land something else next to it and look, we will likely never know precisely why the lander was lost. There were 4 more probes in the Soviet Mars series. Mars 4, lacking a lander, failed to enter Mars orbit due to a computer failure during transit. It managed only 12 photographs as it flew past Mars in 1973 at approximately 1,844 kilometers in distance. Mars 5 successfully reached the planet and entered Mars orbit the next year, but suffered a leak in its instrument compartment, possibly due to micrometeoroid impacts. It operated for only 16 days, returned 180 photos, only 43 of which were of any quality, and managed to measure uranium, thorium, and potassium content on the surface before it went offline. Mars 6 was intended to perform a flyby as well as detach a lander, when while the flyby was successful, the lander again lost contact during descent, shortly before the retro rocket fire. It continued to return data until contact was lost, but a design flaw in a computer chip led to most of that data being unreadable. Mars 7, the final mission of the program, had a similar flyby lander mission profile. The flyby was again successful, but the lander failed to perform a deorbit burn, causing it to miss the planet completely and fly past with the rest of the probe, eventually being flung into orbit of the Sun. This would signal the end of direct Mars exploration by the Soviet Union, with only a few related missions left to mention, a few being from Roscosmos, who took over Russian space exploration following the fall of the Union. For now, we skip back across the ocean for NASA's next Mars program, Viking. Fair warning, from this point forward, each successful mission to Mars is going to get significantly longer. NASA's Viking program grew out of their Voyager program. No, not that Voyager program, the Voyager Mars program, which was planned out as part of the Apollo Applications program, an effort to continue use of Apollo hardware following the end of the Apollo lunar landings. Voyager was an extremely ambitious program, utilizing landers and orbiters large enough to require a Saturn V for launch. I see you, Werner. However, once the AAP was largely cancelled save for the Skylab space station, the program was rebranded into Viking, and made far less ambitious, and therefore much more doable. Much like the later Soviet Mars missions, the 2 Viking missions consisted of both an orbiter and a lander and had 3 simple goals. First, provide new and higher resolution imagery of the surface from orbit, further make sense of what is in the atmosphere and on the surface of Mars, and search for evidence of life, past or present. The Viking orbiter was heavily based on the Mariner 8 and 9 probes. An octagonal bus, 4 solar panels, a propulsion system mounted on one side of the bus, and the landers mounted on the opposite side. Primary instruments included 2 improved Vidicon cameras, an infrared spectrometer for mapping water vapor, and infrared radiometers for analyzing temperature variations. The Viking landers were six-sided aluminum bases with three extendable legs, instrumentation being above and inside that base. They were quite large, 6 by 12 by 10 feet. They had 18 nozzles affixed to them for 3 hydrazine engines used for landing after it separated from its aeroshell and parachute. The fuel was purified in an attempt to keep it from contaminating the Martian surface with earthborne bacteria. Power was provided by 2 RTGs, radioisotope thermoelectric generators, basically nuclear batteries. If you're unfamiliar, RTGs essentially work by harnessing the heat released by the decay of radioactive material and converting that heat into electricity. They're ideal for situations in which not much power is needed, but it's needed all the time, i.e. when the sun isn't shining, making them more robust but a little bit less powerful than solar panels, reliable and consistent, but expensive and require very safe containment procedures. Viking 1 launched on August 20th, 1975. It reached orbit and burned to Mars without any issues, and 11 months later began returning full images of Mars before it entered orbit. Detachment of the lander was delayed, as the initial landing site was deemed too rough, and the orbiter spent most of July 1976 looking for a better site. Once one was found, the lander separated on July 20th, performed a deorbit burn, and turned around to face its heat shield toward the atmosphere. Once it reached an altitude of 6 kilometers, parachutes deployed and the aeroshell was jettisoned. The lander's legs extended, and at 1.5 kilometers, the lander separated, entering terminal descent as it fired its engines. The many nozzles allowed it to make very little changes to the landing site below, spreading the exhaust over a large area and preventing too much surface material from being removed. Viking 1 touched down at a speed of around 2.4 meters per second or 8 feet per second. The lander's legs easily absorbed the impact, and Viking 1 became the first American spacecraft to land on Mars, settling in western Kryze Planitia in the northern equatorial region of the planet. Viking 1 quickly snapped a picture, and over the 4 minutes it took to transmit the image back, excluding the 20-minute journey across the solar system, the lander began activating its various systems, extending its high-gain antenna, and deploying a meteorology boom. Almost every scientific instrument worked perfectly, save for a seismometer that failed to extend, and its sampler arm was stuck due to a jammed locking pin, taking 5 days of shaking the arm back and forth to loosen it until it popped out. Viking 1 operated for 2,245 sols, about 6 Earth years. It was renamed in January of 1981 to the Thomas Much Memorial Station after the late leader of the Viking imaging team. It could have operated much longer, as its shutdown was essentially due to a mistake. On November 11, 1982, a command was sent by ground control that was meant to update the software responsible for charging its batteries. However, it unintentionally wrote over existing data that was used by the antenna pointing software. Contact was lost, and attempts to re-establish the link were unsuccessful, presumably because the antenna had moved into a position where it couldn't be reached. Over the course of its mission, Viking 1 was able to spend a lot of time cataloging the weather of Mars. Individual images and reading from orbit are one thing, but when you have a lander in the same spot for long periods, you can take daily temperature and atmospheric readings, cataloging them over time and finding the patterns within them. In addition, the lander used its robotic arm to scoop 4 soil samples, depositing them into a small chamber with a gas chromatograph mass spectrometer used to analyze the soil composition. The cumulative data was interesting. 2 of the 3 systems responsible for searching for evidence of life within the soil returned a negative result, but 1 returned a positive result. Initially claimed by many to be a false positive, most believe it was a result of inorganic chemical reactions within the soil. At the end of the day, Viking 1's search for life was largely inconclusive, mostly pointing toward negative results, but deemed to not have enough detail to make any sweeping conclusions. Meanwhile, the orbiter sent back over 57,000 images, including close approaches to Phobos. Its orbit was only 300 kilometers above the surface of Mars at its lowest point, but on the high end went up to around 56,000 kilometers, allowing it to pass within 1,600 kilometers of Phobos and take detailed photos of it. All of this was part of the orbiter's extended mission, originally intending to only operate until November of 1976, and the orbiter was officially shut down on August 7, 1980, as it had run out of propellant for attitude control. It performed a total of 1,489 orbits around the red planet. Viking 2 launched 20 days after the first, on September 9, 1975. It went very similarly, arriving at Mars just over 300 days later, and spent around a month orbiting Mars while photographing candidate landing sites and selecting one on September 3, 1976. The lander separated normally, but the bioshield, the portion that connects the aeroshell to the orbiter, didn't eject afterwards, remaining attached to the orbiter, though this didn't really impact its capabilities. The landing procedure went as smoothly as the first, with Viking 2 touching down in Utopia Planitia, a massive impact basin. It landed tilted at 8 degrees, with one leg propped up by a rock that it landed on. Viking 2's mission didn't last as long as the first. While it did exceed its expected lifetime of 90 days, it operated for 1,281 sols, just over half the time of Viking 1. It was turned off on April 12, 1980, after its batteries failed. The orbiter, meanwhile, also exceeded its primary mission, performing close approaches to Deimos, Mars' other moon, taking photos of it from only 30 kilometers away. In the next year, the orbiter's attitude control gases began to leak, and its orbit was pushed higher to keep it from impacting Mars before being switched off on July 25, 1978. The lander's results were similar to the first, though the composition of soil proved to be quite different in this particular location. Abundant amounts of silicone, iron, magnesium, aluminum, sulfur, calcium, and titanium were detected. Some of these chemicals, particularly sulfur and chlorine, were considered likely to be remnants left over after the evaporation of seawater, supporting the notion that Mars did at one time hold liquid water on its surface. Its search for life experiments also revealed the same mostly negative results, with a few likely false positives. While these results were accepted as false positives for a long time, later discoveries would begin to call this into question. But we're not quite there yet. The Viking program was, overall, a massive success, though it would be nearly 20 years before the United States sent another mission that way. In the meantime, we're going back across the world for the final Soviet attempt to explore Mars, or rather, its moons. The Phobos program was carried out in 1988, consisting of 2 probes, both of which had landers to be deployed. These were the final space probes to be designed by the Soviet Union, consisting of an array of spectrometers, an X-ray telescope, a laser experiment designed to vaporize the material on the surface of Phobos to be analyzed by the spectrometers, and a very unique lander, Prop F, often referred to as the hopping lander. Rather than using wheels or skis to move along the surface, this lander would use an inclined piston to throw itself into the air to reach new spots, drilling into the soil at each location to analyze it. Launched only 6 days apart on July 7th and 12th, Phobos 1 and 2 both reached orbit and headed for Mars without any issues. The first spacecraft was supposed to send a transmission back home on September 2nd, but never did. It was realized that the problem occurred on the 28th of August, when a technician left out a single hyphen in one of the keyed commands sent to the spacecraft. This was supposed to be double-checked by a computer that would proofread the code, but it wasn't working at the time, and the technician violated procedure by transmitting the code anyway. This single missing hyphen resulted in accidentally deactivating the attitude control thrusters, leaving it unable to orient itself, and thus depleting its batteries when the solar arrays faced away from the sun. And I'm just going to add that, as someone familiar with computer programming languages, I know this pain, and this is maybe the most frustrating failure in the history of spaceflight. Phobos 2 also began to have issues during its flight toward Mars. By the time it reached orbit of Mars, 2 of its 3 computers were malfunctioning, with one dead completely and the other beginning to fail. This was important because the computers worked as part of a redundant system, requiring 2 to be able to override the decision of one bad computer. Nevertheless, it continued its mission as best it could, gathering data on the Sun, Mars, and Phobos. It executed the final phase of its mission, approaching within 50 meters of the surface of Phobos to release its lander. However, at some point during this approach, contact was lost. Why? It isn't entirely clear. Given the previous computer problems, it's likely that the remaining computer also failed, or was unable to make a decision due to the previous failures. There's also a rather amusing but of course unfounded conspiracy theory in which Phobos 2 was shot down by a Martian defense system that exists on the moon. Obviously silly, but it would make a great premise for a sci-fi novel. The mission officially ended on March 27, 1989, when Mission Control was unable to re-establish contact with the craft. Thus ends the interplanetary efforts of the Soviet Union, though the design of the Phobos spacecrafts would be saved for a later attempt by Roscosmos, though I emphasize that word, attempt. The next 2 NASA missions to Mars would be orbiters with the intention of refining the mapping of Mars's surface, monitoring its weather, and better understanding its magnetic field, as well as determining landing sites for future missions. The first was the Mars Observer in 1992, launched at the end of September. Being over a decade after the Viking program, significant advancements made for a suite of much more powerful instruments to be aboard it, including laser altimeters, a very high-definition camera system, thermal emission spectrometers, and infrared radiometers. However, after a successful launch aboard a Titan III rocket, contact was lost just 3 days before it was scheduled to enter Mars orbit. A likely cause was leakage of fuel and oxidizer vapors through an improperly designed check valve into the pressurization system. Over the course of the flight, these leaked vapors accumulated in the feed lines, causing an explosion when the engine was restarted to perform a course correction. As none of its primary objectives were achieved, most of its science instruments would be used again, implemented on 4 different subsequent spacecraft. One of these 4 was the next mission, the Mars Global Surveyor, in 1996. This was the first step of the larger NASA Mars exploration program under which most future missions, including some still operating today, function. The failure of the Mars Observer prompted NASA to bring all future Mars efforts under one cohesive envelope, each individual mission functioning as a smaller part of the whole. The Global Surveyor featured a number of observers' instruments, including its camera system, laser altimeter, as well as functioning as a relay for later missions to transmit back to Earth. At this point, NASA was attempting to do these missions a lot cheaper, as the high failure rate of Mars exploration was costing a lot of money. As a result, Global Surveyor was launched on the smaller and cheaper Delta II rocket and didn't feature as beefy of an engine to put it into a specific orbit. Instead, a new method was adopted: aerobraking. Already proven to work on the Magellan Venus mission, its principle is very simple. While in an elliptical orbit, the spacecraft can, at its high point, change its orbit to dip the low end into the planet's upper atmosphere. While it passes through, air resistance will then lower the apoapsis, the high point, further refining and circularizing that orbit. This process takes time, comprising the first month of Surveyor's mission in Mars orbit. After that month, it was found that the air pressure it was being subjugated to was bending one of its solar panels, already damaged during the launch, into a backwards position. The aerobraking maneuvers were temporarily suspended while the orbiter drifted into a more ideal sun-facing position, but resumed and finished by 1999, bringing the orbit down to around 450 kilometers at an almost polar inclination, allowing it to pass over the entire planet. In addition to producing incredibly detailed full topographical maps of Mars, Surveyor data resulted in discoveries such as the layered crust of the planet being up to 10 kilometers in depth, produced by centuries of massive amounts of material being moved around on the surface. It found that in some regions, craters had been mostly buried by soil movement, and in others, previously buried craters were now being exposed by erosion. All but the steepest slopes of Mars were found to be covered by a mantle about twice as rich in iron as on Earth. Some areas were covered in an iron oxide material that may have been put in place by liquid water in the past. Dark streaks across the surface were found to be caused by massive dust devils that would make their way across the land, sometimes being captured in action by the imaging system. Regions with Swiss cheese-like holes in the South Pole were found to be widening each year, indicating a possible warming of the region. The overall climate of the planet was found to have cooled since the time the Viking landers were active. Hundreds of gully-like areas were discovered, furthering the case for the past presence of liquid water. The Mars Global Surveyor would continue to operate for just over 10 years, marking landing sites for the next missions and serving as a relay site for those missions. It failed to respond to commands in November of 2006, and 3 days later, a faint signal indicated it had entered a safe mode. After attempts to take it out of that mode failed, the mission was officially ended. It remains in orbit to this day, expected to eventually decay and impact Mars sometime around 2050. In the same year that the Surveyor probe was launched, 2 more lander missions were launched: Mars 96 by Roscosmos and Mars Pathfinder by NASA. Mars 96 had orbiters and landers heavily based on the previous Soviet Phobos landers, but failed to make its injection burn to Mars, re-entering the Earth's atmosphere and disintegrating. Pathfinder, however, was extremely successful and introduced the first use of a method to explore Mars that would become the predominant method going forward: wheeled rovers. Pathfinder continued NASA's attempt to prove that Mars exploration could be done faster, better, and cheaper than before, intentionally using a budget that was only 1/15 the cost of one of the Viking missions. It had a new, unique design. The lander was encased in a set of pedals shaped like a tetrahedron, with solar panels on the inside, capable of putting itself right side up by opening one pedal and pushing if need be. Inside, the instruments included a stereoscopic camera on a pole, a meteorology station functioning as a Martian weather station, and the Sojourner rover, which itself had an X-ray spectrometer. The rover also had 3 cameras, 2 of which were for navigation purposes. Being the first rover, it was quite small, weighing only 25 pounds and being only slightly larger than a toy RC car. Powered by solar panels on its top and communicating with Mission Control via the Pathfinder lander as a relay, it moved about with 6 aluminum wheels with specially developed suspension that ensured all wheels would be in contact with the ground at all times. Pathfinder launched on December 4th, 1996 on a Delta II, arriving at Mars on July 4th of the next year, aiming for a landing site in Ares Vallis, a floodplain in the northern hemisphere and one of the rockiest regions of the planet. It entered the atmosphere inside an aeroshell, deploying a parachute to slow its descent, and when the heat shield released, the lander was lowered on a 20-meter cable, and shortly before it reached the surface, a set of airbags that covered the entire lander would inflate in less than a second. Between 15 and 25 meters from the ground, rockets in the aeroshell fired to slow it further, and the cable was cut, allowing the lander to fall to the surface. It bounced 15 times across the surface, coming back up as high as 15 meters before finally rolling to a stop, conveniently facing the right way up. The airbags deflated and retracted as the lander's pedals opened up, with the rover and solar panels inside. Unfortunately, landing in the Martian night, Mission Control had to wait for daylight to begin operations.
DDL comments report that a signal is barely visible. It's a very good sign, everybody.
Following the success of the landing, the Pathfinder lander was renamed to the Carl Sagan Memorial Station. As pictures and weather measurements began to transmit back, concern arose that one of the airbags hadn't fully deflated, possibly presenting some difficulties in the rover for coming down its ramp to the surface. To fix it, they simply raised one of the pedals and lowered it again, pushing down on the airbag and fully deflating it. On the second day, the rover was released, it deployed into its proper configuration, and backed down the ramp with ease. While Pathfinder began its weather analysis, Sojourner approached a set of 3 rocks with amusing cartoon-inspired nicknames: Barnacle Bill, Yogi, and Scooby-Doo, making analysis of the elements within the rocks and the soil. Remaining within 12 meters of the Pathfinder lander at all times, it would travel a total of 100 meters over the course of its life, intending to last only a Martian week, but instead operating for 92 sols. This would be the beginning of JPL's legacy of over-engineering their spacecraft to outlive their intended lives by a significant margin. Over the course of its mission, Pathfinder sent around 287 megabytes of data back to Earth, including 16,500 pictures and 8.5 million measurements of atmospheric pressure, temperature, and winds. Rock analysis suggested smooth pebbles and cobbles were formed in running water in the past. Water ice clouds were seen in the lower atmosphere early in the morning, and the airborne dust was found to be magnetic, possibly leached out of the crust by a past water cycle. Pathfinder did a lot of work to confirm a more active and life-supporting past, work which would be extended significantly by the following missions. Pathfinder sent its final transmission on September 27, 1997, and communications failed a few days later on October 7th. The mission was officially terminated on March 10th of 1998, after 5 months of attempting to re-establish contact. Repeated charging and discharging of the onboard battery, which was used to heat the electronics, eventually degraded and failed, the same way your rechargeable batteries at home eventually stop working, though the mission had exceeded its goals in the first month and went on to operate for another 2. It would be some time before the next success of the Mars exploration program occurred, and in the meantime we have a few failures and one success to talk about. The first is Nozomi, the first attempt from JAXA, the space agency of Japan, in 1998. An orbiter designed to study the upper Martian atmosphere and plan future missions, it was launched on the third MV launch, a fascinating solid-fueled carrier rocket that lifts off tilted at an angle, unlike most rockets that are entirely vertical at liftoff. After launch, it was sent on a path to fly by the Moon, then returned to Earth and swung by it, the combined gravitational assist and a small injection burn, placing it on a path toward Mars. However, during its Earth assist maneuver, a leaky valve resulted in a loss of fuel, and it was unable to achieve enough acceleration to reach Mars. JAXA quickly reconfigured its mission plan, leaving it in an orbit of the Sun that would result in 2 flybys of Earth, gaining enough momentum to finally perform a flyby of Mars, though it wouldn't be able to enter Mars orbit. In 2003, 5 years after launch, it flew past Mars and went back into orbit of the Sun, with most of its mission having been designated to studying deep space due to the earlier failure. It was shut down in the same year. In the same year as Nozomi's launch, the next phase of the Mars exploration program began, the Mars Climate Orbiter, which would act as a relay for the Mars Polar Lander. However, the Climate Orbiter suffered a unique failure that's almost become a meme at this point. One system on the craft used metric units operated by NASA, and another, built by Lockheed Martin, used Imperial. During its orbital insertion maneuver, contact was promptly lost, and it was realized that the mismatching units caused it to either enter the atmosphere and burn up, or miss the planet completely and swing around into orbit of the Sun. However, despite this failure, the Mars Polar Lander was launched anyway, in an attempt to study the south pole of Mars and search for a possible layer of frozen water that might exist beneath the dust there. With it, 2 probes called Deep Space were intended to impact the surface at high speeds, hoping to study the composition of soil beneath the surface. However, after a successful launch, a successful journey to Mars, and it seemed a successful landing procedure, the lander never spoke back. Communications were never re-established, and the lander was declared lost. In 2001, Mars Odyssey was launched by NASA. The next orbiter to study the climate, risk-assess radiation exposure for human presence, and search for signs of past water or life, Odyssey would also function as the relay for the next 2 landing missions. A complete success, Odyssey currently holds the world record for longest operating Mars spacecraft. When did its mission end? It never did. It remains in orbit and operational to this day, having functioned for 23 years, though it is expected to officially end its mission in 2025. The initial mission ended with the completion of a mapping project in 2004, but was continuously extended when it remained active. It has relayed around 85% of data from missions that followed it, and only one of its 4 reaction wheels have failed in the last 20 years. Its mapping project provided an analysis of basic water distribution on Mars, and would be used for future surface missions to confirm its suspicions of subsurface water. In 2003, a new contender entered the Martian arena, ESA, the European Space Agency. Mars Express was launched aboard a Russian Soyuz rocket containing both an orbiter and a lander, the latter called Beagle 2. It was lauded for its remarkably cheap and simple construction, with the entire lander capable of fitting inside a large backpack if its 100-kilogram mass were no issue. The orbiter, a cube-shaped probe with 2 solar panels and 2 dipole antennas, successfully reached Mars and has been in orbit since late 2003, remaining there to this day. It holds the second-place duration record behind Odyssey, utilizing mineralogical spectrometers, radar altimeters, a high-resolution camera, and acting as a relay for other missions. Its mission continues to be extended due to its discoveries over the years, such as water ice in the polar ice cap, analyzing the composition of the ice being 85% carbon dioxide, images of key tectonic features, performing flybys of Phobos, as well as for its ability to provide communications assistance with further NASA and other missions to Mars. Beagle 2, however, designed to look for signs of life on Mars, did not fare so well. It was structured somewhat similarly to Pathfinder, with 4 folding petals containing solar arrays and communication systems. These petals were themselves contained in a disc-shaped container with a hinged lid, which would allow it to land upside down and then right itself by opening the lid if necessary. Its entry and landing appeared to go nominally, but attempts to contact it afterwards were unsuccessful. For several years, theories were put forth, but there was no conclusive reasoning behind the lander's failure. However, in 2016, a newer orbiting mission managed to find and photograph the lander, stacking several images to get some idea of its status. It appeared that 2 of the 4 petals had failed to unfold, and therefore, beneath one of these petals was the UHF antenna. The lander wasn't talking back because it couldn't, sitting on the surface halfway deployed and inactive. It's possible that it had begun to operate and gather data, but it had no ability to return that data. However, given the incredible success of the orbiter portion of Mars Success, the mission is considered overall to be a success. The next 2 NASA Mars missions are considered iconic, being the ones that were operational for a large portion of my childhood and into my adult life: Spirit and Opportunity. These 2 rovers, called the Mars Exploration Rovers, were dramatically scaled up from the earlier Sojourner, had far more robust scientific equipment, and would impress NASA and the rest of the world for over a decade. They moved with 6 wheels with independent motors, were powered by massive solar panels along the top of the body, and used a host of cameras and spectrometers to analyze the Martian surface. Their landing system was almost identical to Pathfinder. The rovers were enclosed in a tetrahedron of petals that would land with airbag assistance, bounce along the surface, unfold, and allow the rovers to drive out. Their names were chosen through a student essay competition sponsored by NASA. Both were planned to last around 90 sols. Remember that. 3 months were planned on Mars for each. The Mars exploration rovers were launched about a month apart, with Spirit on June 10th and Opportunity on July 8, 2003, both aboard Delta rockets, with Spirit using the heavy variant to give it the extra energy needed to reach Mars. Despite being the second rover designated MER-2, Spirit launched and landed first, touching down in the Aeolus Quadrangle near the equator, rolling into a crater called Gusev on January 4, 2004. It was right on target, and as the lander unfolded and the rover deployed its solar panels and instruments, it began its mission, while the landing site was given a new name, Columbia Memorial Station, in honor of the crew lost in STS-107. Tasked with searching for possible recoverable liquid water, characterizing Martian geology and climate, and preparing for potential human missions, Spirit moved along at a maximum speed of 0.18 kilometers an hour, using its robotic arm at any site or rock that was deemed interesting enough for study. It continued to do this for 1,892 sols, about 20 times longer than its expected lifespan. Part of the reason for the short expected duration was the belief that Martian dust would accumulate on the solar panels and, being unable to clean itself, would slowly drain its ability to recharge itself until it became inoperable. However, it was discovered that sometimes when the Martian wind kicked up hard enough, it would actually push dust off of the panels, increasing its exposure to the sun, and therefore its charging abilities. Spirit functioned nominally until May 1, 2009, when it became stuck in soft sand. This was not the first time it happened, though on other occasions, NASA had been able to perform at-home simulations and instruct the rover to carefully and slowly extricate itself from the sand. However, this time, after almost 7 months of attempting to free it, NASA announced that the rover was completely stuck and would never move again. The rover continued as a stationary science platform until late March of 2010, when it abruptly stopped responding, likely too covered in dust to charge its batteries. The Spirit mission was officially declared complete on May 24, 2011, and a formal farewell for the durable vehicle took place at NASA headquarters. Opportunity, meanwhile, landed on the opposite side of the planet from Spirit on January 25, 2004. The site was Meridiani Planum, a large plain on the Martian equator, and it deployed successfully and began a mission that included discovering meteorites and a detailed exploration of Victoria Crater. Since it never got stuck in the sand, at least not permanently, it significantly outlived its sister rover, surviving multiple dust storms, investigating numerous rock outcrops, and even survived driving into Endurance Crater at an angle of around 30 degrees. After 180 days of exploring Endurance, Opportunity then backed out of the crater, investigated its discarded heat shield about a half-mile from its landing site, then moved on past more craters. In 2005, earlier troubles with the shoulder joint of its robotic arm worsened, the motor stalling due to constant heating and cooling throughout the Martian day cycle. Delivering a higher than normal current to the arm fixed it, but they began stowing the arm in front of the rover during the night. Usually it would be stored beneath the rover's deck, and they worried that it would become completely useless if it were to stop moving entirely. In 2009, Opportunity moved on towards Endeavour Crater, the lengthy journey being constantly interrupted by more meteorite investigations, as well as sand dunes deemed too difficult to traverse, requiring the controllers to find a way around them, and avoid a repeat of Spirit's demise. It arrived at the crater rim in 2011, and it was decided that rather than enter the crater, it should drive around the rim, lacking any unique-looking material within to necessitate possibly getting the rover stuck there permanently. It would explore the area around the edge of this crater for the remainder of its life, traveling a total of 45.16 kilometers over the course of its entire mission. In 2014, it suffered a curious amnesia event in which it began writing data to memory that would then erase that data, eventually needing to reset it in such a way that it would ignore that volatile memory source entirely. In June of 2018, Mars was enveloped in a massive planet-wide dust storm. To prepare for this, Opportunity was shut down into a power-saving mode, which would periodically check the solar panel's ability to draw power and bring it back online when it detected sufficient sunlight. However, after the storm subsided, Opportunity remained silent. The team was hopeful that a windy period in late 2018 would clear some of the dust, enough to bring it online, but this never happened. Opportunity's last transmission indicated diminishing power levels and sunlight exposure, and one journalist translated this transmission in a way that tugged at the heartstrings of the world. "My battery is low, and it's getting dark." though of course Opportunity never actually directly said these words. After thousands of recovery commands, NASA said its goodbyes to the still silent rover. Associate Administrator Thomas Zurbuchen said on February 18, 2019, quote, "It is therefore that I am standing here with a deep sense of appreciation and gratitude that I declare the Opportunity mission is complete." It lasted a grand total of 5,352 souls, 15 years on Earth, just a little bit past its 90-day expected lifetime. It is often regarded as one of NASA's most successful ventures. Now, what about scientific findings? Together, the MER program all but confirmed that Mars used to hold liquid water through analysis of rock alteration and deposited mineral content. Martian geology was further refined, figuring out precisely what resources exist within Martian rock, where they are, and how they likely got there. Microscopic images of the soil revealed small granules in a spherical shape, yet another piece of evidence that water once existed to polish and smooth out these granules over time. Opportunity managed to make the first full temperature profile of Mars, with the rover measuring up to 6 kilometers high and the Mars Global Surveyor measuring further up in the atmosphere. Spirit took the first photograph of Earth from Mars, as well as making multiple observations of the moons of Mars during solar transits when they passed in front of the Sun. The two rovers laid the groundwork for future missions to search for ancient biospheres and narrowing down where life might have once existed on Mars, if it ever did. Quite frankly, I could make an entire video just about the specific discoveries made by the MER program. However, it would simply take too much time to cover it all here. We must move on, but perhaps one day, the specifics of all these findings may be discussed. Long before the MER program ended, NASA launched its next mission, the Mars Reconnaissance Orbiter. This probe would play a key role in determining landing sites for the next missions, utilizing its HiRISE camera being the largest telescope of any deep space mission in all of history. Use of this camera also enables the MRO to perform its own scientific research on the surface all the way from orbit using subsurface radar and spectrometer instruments, as well as provide unprecedented images of activity on the surface. The MRO was launched on August 12, 2005 on an Atlas V rocket, arriving at Mars in March of 2006 and using aerobraking to enter a stable, circular, near-polar orbit. During its mission, it has found that new impact craters on Mars have dug up water ice, nearly pure, which then sublimates away in the Martian weather. Chloride deposits, which were also found by the Global Surveyor and Mars Express with their data combined, suggest the deposits were formed when mineral-rich water evaporated there. Recurring slope lines photographed over time appear to have been caused by water beneath the surface flowing through the ground, though further research is currently calling this notion into question. As of today, the MRO continues to operate, third in line for longest operating Mars probe, behind Mars Express and the Mars Global Surveyor. The next surface mission would be a stationary lander, Phoenix, launched in 2007 aboard a Delta II. Intended to study the geological history of Mars and attempt to understand the history of Martian climate change, Phoenix carried a number of instruments that were carried over from the failed Polar lander, as well as some from a cancelled 2001 lander called Surveyor. It featured a trench-digging robotic arm, a set of chemistry laboratories for samples to be placed in, as well as several microscopes. You may wonder, after 3 successful rover missions, why was Phoenix stationary? There's a few reasons. The area it was intended to land in was considered fairly uniform. The ability to travel wouldn't result in many new discoveries, as it was all more or less the same. Furthermore, the budget that would be needed to make it a mobile lander could instead be allocated to more advanced instruments, making it a more focused, though in a way less versatile, program. Several steps were made in preparation for Phoenix's landing. First, Mars Odyssey located hydrogen signatures on Mars, and these were used to determine its landing site, as the only way for hydrogen to exist on Mars would be water in the form of subsurface ice. Second, the 3 active Mars satellites, the MRO, Odyssey, and Mars Express, all made small adjustments in their orbits to ensure that they would be over Phoenix's landing site as it made its descent towards the surface. As a result, we now have this remarkable image, the first time a spacecraft was ever photographed by another while landing on another planet. Being relatively small and light, Phoenix used a very simple landing system similar to that of Viking. A parachute slowed its descent somewhat as it fell within its aeroshell, and the shell jettisoned to allow Phoenix to separate, fire 8 small engines to slow it down to a speed where it could touch down, and did so nominally, though the parachute deployed 7 seconds after it was supposed to, resulting in Phoenix being just on the edge of its intended landing zone of Green Valley, the largest lowland region of Mars. It then deployed its circular solar panels and began its mission. Among the first things noticed was the ground directly beneath it. With the top layer of dust blown away by the lander's thrusters, Phoenix used its robotic arm to photograph the area, finding it to be a smooth, bright surface that was determined to be water ice. It then began to use the arm to dig trenches, examining the clumps of bright material underneath and watching as they slowly evaporated over the next 4 days. More water ice. Having confirmed its original mission goal, Phoenix went on to try and determine how long water could exist on the surface after sublimating from ice, and whether this would be enough to support life processes. It then began scooping more soil and delivering it to its onboard laboratories, determining the soil's salt and acidity levels. NASA was hoping that Phoenix would survive into the Martian winter so that it could observe the formation and spreading of polar ice. However, as it entered a period of expected low sunlight exposure, it was put into a safe mode that also involved shutting off the heaters that kept the equipment warm. As winter came to an end, the craft was brought out of safe mode, but had lost use of most of its instruments. Shortly afterwards, after 152 sols, again 3 times its expected length, loss of contact with Phoenix was confirmed, and its mission was officially concluded in November of 2008. You may have noticed it's been a little while since we talked about a Mars mission that failed. Well, get ready. The next mission was a new collaboration, Phobos Grunt, a Roscosmos attempt to return a soil sample from Phobos, and also carried Yinghuo 1, the first Chinese Mars lander. It was largely newly developed, though some inspiration was drawn from the Soviet Luna program, which did successfully return lunar soil to Earth in the 1970s. Phobos Grunt had a lengthy and complicated development process, being delayed several times before finally being launched on a Zenit rocket in 2011. However, its Mars insertion burns never occurred, and attempts to reactivate the craft failed before it plunged into the Pacific Ocean in an uncontrolled re-entry the next year. Next to the plate was the Mars Science Laboratory, an ambitious and all-new rover which required an ambitious and all-new landing system. Initially proposed in 2003, the MSL spent a long time in development, suffering significant delays and cost overruns in the range of $400 million. To compensate and meet the intended launch date, several instruments and cameras were simplified or altogether removed, and the finished product was named via a public poll on the NASA website, Curiosity. A much larger and more robust vehicle than ever before proposed, Curiosity weighs nearly 2,000 pounds, is the size of a small car, and is powered by an RTG rather than solar panels. Its advanced twin onboard computers are designed to protect against extreme radiation and to keep data intact during power-off periods, as well as featuring several times the power of the Mars exploration rovers. Its 6 wheels have an advanced suspension system that double as landing gear, and you'll find out why it needed this in a moment. It features a host of spectrometers, sample analysis tools, and a suite of 17 cameras, including one specifically made to photograph the rover's descent toward the surface. One of the more interesting aspects of Curiosity's design lies within its wheels. Take a look at this and tell me what you see. I'll give you a moment to think about it. That's right, it's Morse code. As Curiosity moves along the surface of Mars, it leaves a message in the soil from its creators, 3 simple letters, JPL, the NASA Jet Propulsion Laboratory. Over 60 potential landing sites were evaluated for Curiosity, and in 2011, Gale Crater was chosen, a possible dry lake just south of the equator. Curiosity was launched on an Atlas V on November 26, 2011, preparing for a landing with higher precision than ever before that would occur in August of the next year. Despite occurring late at night in the United States, 3.2 million people tuned in to watch Curiosity perform its elaborate descent to the surface of Mars, done completely autonomously, while Mission Control simply watched and waited for news from 20 minutes ago. Curiosity entered the atmosphere enclosed in an aeroshell, using a precision-guided entry system to keep itself on course to its very small target landing zone. Much of this precision was achieved with an algorithm derived from the same one used on the Apollo command modules when they returned to Earth, which used the lifting force experienced by the aeroshell to detect errors in range and adjust its entry angle accordingly. It was also able to eject extra mass in the form of tungsten ballast weights shortly before atmospheric entry. At about 10 kilometers above the surface, after the entry phase was complete, a parachute 16 meters in diameter was deployed, much as with previous missions. Once again, the MRO was able to capture a remarkable photo of this part of the sequence. Despite the massive parachute, Curiosity was still falling at a rate of around 100 meters per second when the rover and its descent stage dropped out of the aeroshell at 1.8 kilometers, firing a set of 8 hydrazine thrusters to further slow it down. However, there was concern about these engines kicking up dust on the surface that could damage Curiosity's instruments, and for this reason, the next step was the Sky Crane. A system of cables lowered the rover from a height of around 7.6 meters while the engines kept the descent stage in a hovering position. The rover's wheels moved into landing position and touched down extremely gently, waiting a second to detect weight on the wheels and confirm that it was on the ground. Then the umbilical cords and tethers were cut, and the descent stage flew up and away, crash landing at a safe distance of 650 meters away. Curiosity was successfully on Mars, exactly where it was supposed to be.
Yep. UDLCom configuration.
RIMU stable.
UHF telemetry.
RIMU stable.
UHF is good. Touchdown confirmed. We're safe on Mars. Time to see where our Curiosity will take us.
Curiosity spent several days calibrating and testing its instruments, ensuring everything was in working order before ground teams identified possible routes to the base of Mount Sharp, a mountain in the very center of Gale Crater. A mission plan of spending a year studying the rocks and soil on its way was formed. Curiosity first moved its wheels on August 29, 2012, 23 days after landing, to an area where 3 different kinds of terrain intersect, spending a month studying the area. By the end of September, Curiosity had found evidence for an ancient stream bed, the composition of which suggested water once flowed quite vigorously here. In October, it performed its first soil analysis, finding the presence of minerals that was similar to basaltic soils of Hawaiian volcanoes. By the next year, Curiosity made the first test of its drilling system, finding the conditions of the sample were once suitable for microbial life, with water, carbon dioxide, oxygen, sulfur dioxide, and hydrogen sulfide present. At the end of February, the rover was forced to switch to its backup computer. The primary computer had a problem with its flash memory and was continuously rebooting itself, stuck in a programming loop. After the backup computer was turned on in safe mode, it was deemed safe to make the switch, and the rover was considered operational again in March. In June, it was officially announced that its journey to Mount Sharp would begin. By July, it had traveled a total of 1 kilometer across Mars, and then in August reached a milestone of 1 year on Mars. To celebrate, NASA programmed the rover to sing happy birthday to itself, though it didn't actually play any sound exactly. More specifically, the resonator on the sample instrument was programmed to vibrate in a way that matched the tones of the song. By the end of 2013, findings from Curiosity included confirmation of what was once a freshwater lake, which could have been a home for microbial life, as well as the existence of organic material, being carbon, that could not be a result of Earth-borne contaminants. While possible that this could come from meteorites, NASA considered it not likely, and that the carbon most likely originated on the planet. On September 11, 2014, Curiosity officially reached the slopes of Mount Sharp and began further studies there, having traveled a total of nearly 7 kilometers from its landing site at this point. It continued to obtain detailed data about how the landscape of Gale Crater might have changed over the years, leading to theories that much of the water there had been lost before the lake bed had even formed, being regained afterwards, then lost again. In the next year, NASA collaborated with Microsoft to develop OnSite, a software tool that uses the rover's real data to create a 3D simulation of Mars, allowing scientists to interact with the environment in virtual reality. People were now able to examine the rover's worksite from a first-person perspective, making them better suited to planning new activities and preview the results of the rover's work. Having already outlived its primary mission, NASA continued to find new tasks for the rover, studying various areas around the base of Mount Sharp. Curiosity continues to work to this day, though it briefly lost use of its drill, survived multiple dust storms, and had chunks taken out of its wheels over the years by the rough terrain. It is on its 4th extended mission, which began in 2022, has been on Mars for over 4,000 sols, and currently shows no signs of slowing down or stopping. Let's go back in time a little bit. Fair warning, we're going to do this a few times from here on out. In 2013, another country added its name to the list of those that have explored Mars, India. The Mars Orbiter mission, ISRO's first interplanetary mission, marked the 4th space agency to achieve Mars orbit after NASA, Roscosmos, and ESA, and the first agency to do so on their very first attempt. In true ISRO fashion, the probe is also the cheapest Mars mission to date, costing around $73 million US. The Prime Minister of India at the time joked that the mission cost less to perform in its entirety than Hollywood spent on the then in-production film Gravity, which had a budget between $80 and $130 million US. The probe was a simple cube-shaped bus with a single solar array and included a thermal imaging spectrometer, a color camera, a mass analyzer, a methane sensor, and a photometer to measure deuterium and hydrogen in the upper atmosphere. In some ways, the mission functioned as a proof of concept to develop the technologies and techniques for planning and operating an interplanetary mission, with the science objectives being considered secondary. The Mars Orbiter mission was launched on India's own PSLV or Polar Satellite Launch Vehicle on November 5, 2013, and arrived at Mars in late September of the next year. It lasted just under a decade, with communications being lost on October 2, 2022. It had entered a 7-hour eclipse period that April, which it was not expected to survive, and following the loss of communications, ISRO officially announced that the mission was concluded due to loss of fuel and battery power. In the same year as ISRO's mission launched, NASA launched its next and third orbiting spacecraft that remains active to this day, MAVEN, standing for Mars Atmosphere and Volatile Evolution. Specifically designed for study of the Martian atmosphere, MAVEN's mission is to examine the loss of gases from the atmosphere of Mars into space due to solar winds, which will help to better understand the planet's history and how its climate reached the point it's at now. Instrumentation includes a solar wind electron analyzer, a solar wind ion analyzer, and tools to measure thermal ion composition and solar energy particle impact. MAVEN launched on an Atlas V in November of 2013, reaching Mars and entering an elliptical orbit in September of 2014. It would be another full year before it was fine-tuned to start its primary mission, and at that time, a comet was approaching Mars, forcing researchers to maneuver it out of the way to avoid any harmful effects from it, though they did manage to perform measurements on all the dust and gas expelled by it. Following completion of its primary one-year mission, MAVEN had to perform an emergency maneuver to avoid colliding with Phobos, then later lowered its orbit to better serve as a communications relay for landed spacecraft. It suffered a failure of its inertial measurement units in late 2021, which are needed for it to maintain orbit and attitude, but it was reprogrammed to use star positions to do its measurements after a period in 2022 where it wasn't used for science or relay activities. MAVEN continues to operate today, with all instruments fully functional, and is expected to last until at least 2030 with its current fuel reserves. Next up, ExoMars. ESA made its second foray into exploring Mars in 2016 with a program that consisted of 4 parts, which were to be delivered as 2 separate payloads. First, the Trace Gas Orbiter, constructed in collaboration between ESA and Roscosmos, is intended to better study methane and other gases present in the atmosphere that could indicate biological activity. It uses a suite of instruments from spectrometers to a color and stereo surface imaging system to a neutron detector for finding hydrogen, as well as providing relay capabilities for the rest of the ExoMars program. Speaking of which, the Schiaparelli lander, named after a previously mentioned Italian astronomer, was carried with the Trace Gas Orbiter. Consisting of a disc-shaped bus with instrumentation, power, and communication systems located on top, the lander was mostly a technology demonstration for future soft landings, but did have a limited science payload designed to measure Martian weather, particularly dust storms. The third and fourth parts of the ExoMars mission was the Kazakok lander, a Russian-built lander that would deliver the Rosalind Franklin rover owned and operated by ESA, which is a medium-sized rover comparable to a Mars exploration rover. However, after the 2022 Russian invasion of Ukraine, ESA voted to suspend cooperation with Russia, placing the rest of the ExoMars project into development hell for the time being. The first half of ExoMars, the orbiter and Schiaparelli lander, launched in March 2016 aboard a Russian Proton carrier rocket, successfully reaching Mars in October of the same year after 2 mid-course corrections during its cruise phase. The lander was disconnected before orbital insertion, intending to hibernate for 3 days while it headed for atmospheric entry. Protected by a heat shield, entry went normally, but at some point after it reached subsonic speeds, its parachute disconnected early, preventing its retro rockets from slowing it down to a good soft landing speed. The lander crashed into the Martian surface at 300 kilometers an hour, which the nearby Opportunity rover attempted to capture images of, but it was too far off to be seen. Its crash site was, however, photographed from orbit by the MRO, suggesting a fuel tank may have exploded on impact and showing parts strewn around the crash zone. Fun fact that I learned about while writing this script, thank you Aaron, the company responsible for testing the lander's parachute system was ARCA, the same company currently responsible for multiple failed spaceflight ventures such as the water-fueled Eco rocket. However, amusing as that is, the parachute itself wasn't directly responsible for the lander's failure. It was more directly related to the inertial measurement unit, which suffered oversaturation of telemetry when the craft started rapidly rotating after parachute deployment, resulting in an incorrect measurement of the altitude and an early release of the parachute. The Trace Gas Orbiter, on the other hand, reached Mars without issue, using aerobraking to enter an elliptical orbit of 200 by 1050 kilometers, then using small thruster firings to raise itself into a circular orbit of 400 kilometers all the way around. Like many recent missions, TGO continues to operate, mapping a broad list of atmospheric gases on Mars and trying to determine whether these gases are a result of geological processes or something else, like biological processes. Its work has resulted in multiple findings such as water ice cloud enhancement during dust storms, new measurements of atmospheric thermal structure, an estimate of the time span of the climate record for the South Polar ice sheet, and for dry processes being responsible for slope lines previously thought to be caused by subsurface water. In April 2019, ESA reported that TGO had detected no methane whatsoever in the atmosphere of Mars. Now that a few missions have been dedicated to better understanding the atmosphere of Mars, NASA's next effort would be aimed in the opposite direction. InSight, the interior explorations using seismic investigations, geodesy, and heat transport lander, was launched in 2018 aboard an Atlas V. The last stationary Mars lander to be deployed by NASA to date, InSight used seismic instruments, a heat flow probe that burrowed into the ground, a radio science experiment that measures planetary rotation, a weather experiment, a laser retroreflector, and 2 instrument cameras to monitor these experiments. A full-scale engineering model of InSight was also built, called Foresight, which was used to test its instruments on Earth and fine-tune the actual craft before it was prepared for launch. InSight arrived at Mars on November 28, 2018, descending into the atmosphere enclosed in an aeroshell, then separating and deploying a parachute, making its final descent with small rocket engines much like Phoenix and Viking did. A few hours later, Mars Odyssey relayed signals from the lander that it had successfully deployed its solar panels and was functioning nominally. Its landing site, which was relatively arbitrary given that its goals were beneath the surface and not related to the actual surface features, was Elysium Planitia, near the equator and south of the volcanic region of Elysium. On December 9th, InSight recorded Martian wind in the audible spectrum for the first time in history, allowing the world to hear what it sounds like to stand on Mars. A few days later, it deployed its seismometer via a robotic arm, then placed a wind and thermal shield over the seismometer, and spent several years measuring vibrations in the surface, recording frequent active quakes and magnetic pulses, the latter of which was rather unexpected. In 2020, NASA noted that the magnetic field of Mars was about 10 times stronger than previously thought and fluctuates rapidly. The next year, in April, with its solar panels completely covered in dust, InSight went into hibernation mode, but woke up only 2 days later, transmitting images back of the state of its panels. The team used its robotic arm to scoop up some sand and trickle it onto the panel so that it would blow away after sticking dust particles to it, reducing the overall dust coverage on the panel. This maneuver boosted the power of InSight by 30 watt-hours per sol. By 2021, 3 papers were published studying Mars's interior structure using data from InSight. The lander confirmed that the center of Mars is molten and the crust is thinner than expected, existing in 2 or 3 possible sublayers. In 2022, InSight went into safe mode to protect from a dust storm, shutting down all but essential functions, but came out of safe mode by the end of that month, resuming normal activities. By May of 2022, InSight had recorded 1,313 quakes beneath the surface of Mars. The heat flow probe, meanwhile, started digging into Mars back in 2019, though it only made it about 1.1 feet. Several attempts were made to dig further, but the effort was eventually given up as a failure in 2021. JPL researchers concluded that Martian soil doesn't provide the needed friction for drilling, causing the probe to simply bounce around and widen the hole in which it was attempting to dig. At one point, they attempted to use the scoop on the robotic arm to better push the probe into the soil, even dumping soil into the hole to increase friction, but were unable to get it deep enough to take proper measurements. By May 2022, NASA decided that there was simply too much dust on the solar panels to continue the mission. InSight was receiving about a tenth of the power it received on landing, and it was put into a low power mode in July. By the end of the year, InSight had stopped responding to communication attempts, and the mission was declared officially over. Yet another new contender entered the Martian arena, the United Arab Emirates. Borrowing launch capabilities from a Japanese H-2A rocket, the Emirates Mars mission launched in July 2020, arriving at Mars in February of 2021. Consisting of a probe called HOPE, the mission's goal consisted of studying both daily and seasonal weather cycles, as well as how that weather varies in different regions of the planet. A collaboration between both the UAE Space Agency and the Mohammed bin Rashid Space Center, HOPE remains one of several probes active around Mars today in a relatively high polar orbit, with the team behind it referring to it as the first true weather satellite at Mars. While others are capable of weather monitoring, HOPE is the only one fully dedicated to that purpose. Due to its high orbit, HOPE has also been able to take remarkably detailed images of Deimos, such as this one. The next mission to Mars would also see a new country to successfully orbit and land. Tianwen-1, a Chinese spacecraft consisting of an orbiter as well as the Zhurong rover, launched aboard a Long March 5 in July of 2020. Tianwen-1 has at least one unique feature that I really appreciate, something China has gotten very good at doing, having deployable cameras to give us a view outside of onboards as if we're standing beside the crafts observing them. The first of these cameras was deployed while the probe was on its way to Mars, showing the hexagonal bus, solar arrays, antenna, and the aeroshell containing the lander and the rover. Tianwen-1 entered Mars orbit in February of 2021, spending several months scanning and imaging the surface to find an ideal landing zone. During this time, it also released a second camera, providing the first images of a satellite orbiting Mars from a third-person perspective. The lander detached in May of 2021, and because it was relatively light, was capable of using the same landing method of Viking, Phoenix, and InSight. It entered the atmosphere in an aeroshell behind a heat shield, which then jettisoned and a parachute was deployed, and near the surface the parachute was cut, and the lander used retro rockets to make its final descent to the surface. It successfully touched down in the southern portion of Utopia Planitia, spending several days preparing the rover before it drove down the lander's platform onto the Martian soil. In June, Zhurong dropped another camera and then drove away from it, allowing it to take an image of the rover and lander on the surface. Of similar design but slightly smaller and lighter than the MER rovers, Zhurong's activities on the surface have been somewhat mysterious due to the CNSA's tendency toward maintaining secrecy. In 2023, however, Chinese scientists did publish a Mars weather report based on its data. In the previous year, the rover entered hibernation mode to protect against both the Martian winter and an approaching dust storm, and appeared to not wake up afterwards. As near as we can tell, while it has outlived its expected lifespan, Zhurong's solar panels are too covered in dust to maintain power, and it has not moved since it went into hibernation. The orbiter, however, remains active and functional, one of 7 spacecraft continuing to orbit Mars to this day. At the end of this battery of 2020 missions, NASA launched its most recent, Mars 2020, consisting of a new rover, Perseverance, and an all-new vehicle, the Ingenuity robotic helicopter. With a design heavily derived from Curiosity, Perseverance holds many similar instruments, as well as several new ones, including some that had to be cut from Curiosity due to time and budget constraints. One of these is the ability to drill sample from Mars that will be left in containers along its route for retrieval by a future sample return mission, something we'll come back to. Ingenuity, meanwhile, was something of a proof of concept. Consisting of 4 landing legs attached to a cuboid bus, it used 2 4-foot-long rotors, needing to spin at an extremely high rate of 2400 to 2900 RPM to maintain flight in the thin Martian atmosphere. Above the rotors is a small solar panel used to recharge its batteries. Perseverance didn't have a Morse code message hidden in its wheels, but instead had a new message which went completely unannounced, but it was quickly decoded only hours after the video of its landing was released by space fans online. It's right here, hidden within the rover's parachute. Do you see it? Spelled out in binary code is the phrase, "Dare Mighty Things," a kind of JPL motto adopted by a speech by Teddy Roosevelt. On the outside of the ring is GPS coordinates leading to the entrance of the JPL Visitor Center. A second, less subtle message is embedded on the body of the rover itself. A family portrait depicting Sojourner, Spirit, Opportunity, Curiosity, and finally, Perseverance and Ingenuity. Launched on an Atlas V on July 30th, 2020, Mars 2020 arrived at Mars in February of 2021. The landing sequence was similar to Curiosity, utilizing an aeroshell and parachute and a sky crane for final descent. At the same time, the InSight lander was still active on Mars, and the team attempted to use it to detect parts of the landing from 3,400 kilometers away. However, InSight never felt anything, indicating a very low seismic efficiency of Mars. After landing, Perseverance quickly began surface operations, sending images back to Earth and confirming that Ingenuity was still on board and functioning.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
The helicopter was deployed on April 3rd, waiting as the rover drove away from it and making its first flight on April 19th. At this point, its mission was complete. Its entire purpose had been to prove that atmospheric flight on Mars was possible at all, and it had now done this. However, it would continue to make test flights of up to 90 seconds at a height of 10 to 16 feet off the ground. Intending to only make 5 flights, Ingenuity would go on to make a remarkable 72 flights, scouting areas of interest for Perseverance and exploring the limits of what it could actually do. On January 18, 2024, Ingenuity made its final flight when its rotor blades were badly damaged upon landing, permanently grounding it. It flew for a total of 2 hours and 8 minutes, covering more than 17 kilometers as it followed the progress of the nearby rover. Perseverance began its science campaign in June of 2021, acquiring its first sample from Jezero Crater in August. By now, it has collected 24 of 38 samples, completed its first, second, and third campaigns, and is currently on its fourth, the Margin campaign. The majority of its time has been dedicated to searching for signs of ancient life, as well as sampling the soil, and thus far, no signs of definitive life have been found. The rover remains in good health, however, and is expected to undertake a fifth campaign sometime in 2025. You may have noticed a lack of significant findings from this mission. Most of the reason for that is that it's still ongoing. A lot of the data obtained by Perseverance has yet to be properly studied and published about. Within the next couple of years, we'll know a lot more about everything that particular rover has found, as well as possibly have a solution to the problem of returning samples. For now, we do know that the history of water in Jezero Crater is much more complex and dynamic than originally thought, including evidence of major flooding late in its life that carried large boulders into the crater. Perseverance also used an instrument called MOXIE, standing for Mars Oxygen In Situ Resource Utilization Experiment, which took carbon dioxide out of the Martian air and produced pure oxygen. Though it is merely a proof of concept, it does provide proof that we can in fact create our own resources on Mars once we get there. The subject of returning the samples being left on Mars currently by Perseverance is in itself something of a big topic. The initial plan was for a joint NASA-ESA program, which was approved in September of 2022. It consisted of 2 separate phases. First is the sample retrieval mission, which would utilize a lander with a sample transfer arm, 2 Ingenuity-class helicopters which would collect the samples along with Perseverance itself, and a small Mars ascent vehicle. The proposed return lander is quite large, being double the mass of Perseverance, and will need enhanced landing navigation to ensure that it can accurately touch down close to the rover. Once Perseverance and the 2 helicopters collect the samples, it will use the ESA transfer arm to place them into the sample return capsule of the ascent vehicle. The Mars Ascent Vehicle, or MAV, is a small 2-stage solid-fueled rocket that will then carry the samples from the surface of Mars up into orbit to rendezvous with the second phase of the program, the Earth Return Orbiter. This was planned to utilize a unique launch method, being catapulted off of the lander 21 feet into the air before igniting its engine and heading out of the atmosphere. The reason for this is simple. It will keep the ascent vehicle's engines from tipping the sample return lander over during ignition. Its second stage would be spin stabilized due to the unknown factor of the samples creating a possibly uneven distribution of weight. Once reached by the Earth Return Orbiter, the sample return capsule will be enclosed inside an Earth entry capsule, and the orbiter will return to Earth, likely using ion propulsion which, while slower, is far more efficient, allowing the vehicle to take a large amount of fuel to Mars to be used in returning to Earth. The Earth entry capsule will then land passively without a parachute and be recovered and taken into a clean environment for examination. As of November 2023, NASA announced that the sample return proposal was officially paused, citing a review critical of its high cost and complexity. In January of 2024, the Mars Sample Return Program came under intense scrutiny due to its incredibly high cost of around $11 billion US. With its current budget, NASA considered the proposal to be infeasible. Official requests were sent out to JPL and others for alternative sample retrieval proposals, with private industry writing up their own 90-day studies on how to do it easier and cheaper. Lockheed Martin, Northrop Grumman, Aerojet Rocketdyne, SpaceX, and others are now all in the running for cost-effective alternatives to pick up the samples left by Perseverance, though the project is, at this time, very much still in the air. So, after sample return, what's next when it comes to exploring Mars? Well, there are a suite of missions currently being proposed and planned. NASA plans to launch 2 orbiters, Blue and Gold, on the ESCAPADE mission in September of 2024, using Blue Origin's upcoming New Glenn rocket. ISRO is planning a sequel to their Mars orbiter mission, JAXA is planning a sample return mission to Phobos, and the CNSA is also planning Tianwen-3 with hopes of returning its own samples from Mars. But what else? Well, the obvious is quite a large step, almost 1,000 times larger of a step than the Apollo astronauts ever took. The idea of landing people on and even colonizing Mars is far from a new one. Pioneering rocket scientist Dr. Wernher von Braun, while he was working in Germany in the late 1930s, threw a costume party with his team that was themed as the first German dinner party on Mars. Of course, back then, we knew absolutely nothing about the conditions on the surface of Mars, but that didn't stop people from dreaming. Early crewed Mars landing proposals often utilized lifting bodies, landers that would use aerodynamics to land like the Space Shuttle did, relying on the assumption that Mars had a fairly thick atmosphere. These designs would change dramatically once the first probes began to return data about Mars's thin atmosphere and general weather and geology. Concepts for Mars habitation focus on living within artificial habitats with complicated methods for life support. Despite being extremely ambitious, this might not be the worst of the problems. The lower gravity on the surface would, over time, weaken bones and muscles and put colonists at risk for osteoporosis and cardiovascular problems. The weak magnetosphere of Mars also allows further radiation to reach the surface, which can be mitigated, but it is difficult. At the bottom of the list of problems is psychological effects, concerns regarding the results of isolation, repetitive tasks, and living in close quarters with others for years at a time. The distance to Earth renders instant communications impossible. At best, we on Earth will know there's a problem on a Mars colony about 20 minutes after it actually happens. Some proposals have involved placing colonies within caves or lava tubes below the surface, thereby mitigating radiation and the risk of asteroid impacts. Others propose burying the habitats themselves for the same reasons. This is another topic I could spend hours expanding upon, and perhaps someday will in a separate video, but for now, this video is getting a little long in the tooth. I don't know precisely how or when man will land on Mars, or how long we will stay when we get there, but it feels to me like an inevitability. Humanity is an expansionist species. We spread to every region we're capable of. We've settled lands that could, by some standards, already be considered inhospitable. We cannot be stopped. We will go from the Moon to Mars and beyond. While interstellar travel remains beyond our current grasp, that is another hurdle we can, eventually, overcome. Our solar system has a ticking time bomb at its center, and while we have a long time yet to go, we will need to make this first Martian stepping stone before we leave altogether. For the long-term future of humanity, we must land on Mars. Only then will we be able to continue further. Ad astra per aspera. Through hardship to the stars.